So in this graphing data lab analysis, I'm basically just going to explain how we met our objective in this lab and the steps that we took to, get to graph this and come up with the best answer to the objective. So this objective was basically to find the relationship between how high we would drop a golf ball to how high it would bounce back up. So after running the experiment with 3 trials at 5 different points on the meter stick, I was able to then graph my results. So on the x-axis, which is I used as the drop height, I graphed 20, 40, 60, 80, and 100 centimeters because that's how high we dropped the golf ball from. And I did increments of obviously 20. And then on the y-axis, I did the bounce height because that is the dependent variable, because obviously it depends how high you drop the ball from. That's how high it goes up. So that's my bounce height, and I did 5 increments all the way up to 71.3, or 71 because that was our maximum height. So we ran the lab, and then I was able to, obviously plot the points. So for example, at 20 centimeters, ours came back at 17.3. And then at 40 centimeters, the ball bounced back up to 29.3. So, and so on and so forth, all the way up to 71.3 at 100 centimeters. So then once I had those 5 points plotted, I basically, in order to find the line of best fit, I freehanded a straight line that went right through all the points, or as accurately as I could, through the points, and then I assigned that the line of best fit. So obviously I had to find the equation for that line, to find the slope. I tried to find points that would cross directly with my graph paper as accurately as possible. So I chose these 2 points here. So this point here is 45, 35, and this point here is 80, 57.5. So basically I just found the slope between those 2 points because they're both on the line. So the change in y I found is 57.5 minus 35, which gives you 22.5. And then for the change in x, I did 80 minus 45, which is 35. So now that you have those 2, you can basically just go to your slope, which is the change in y over change in x. So 22.5 over 35 on a calculator is 0.64. That's your slope of this line. So to create it into y equals mx, or plus b, y-intercept form, slope-intercept form, sorry, you assign y, so I took this point because it's smaller, so your y value is 35, equals your slope, 0.64, times x, which in this case would be 45, sorry, down here, plus b, because you don't know what b is. So after you do the algebra, using a calculator, you solve, and you get 6.2 as your y-intercept. And if you look down here, that's pretty accurate, because right where this line crosses, that's about 6, I would say, maybe 6.5, something like that. So that was pretty accurate, I think. So then once you have that, you can just plug it into the slope-intercept form. Y equals 0.64, where is it, right here, x plus 6.2, and that's this line. That's your line of best fit. So obviously there are many sources of error that could have happened with this lab. I mean, when we ran the lab, we basically just estimated how high the ball would go up. We didn't really have precise measurements since it all happened very quickly. So all of our they're basically just estimates, whole numbers. So that could account for a lot of the inaccuracies. But also this line of best fit that I drew, I did that freehand. So that's obviously, I just drew that as best as I could that would incorporate all these points. But there could be, it could be a lot more accurate. So that's definitely, source of error. And for our graph, these increments, I kind of just made those up that would fit the page the best and that would incorporate everything on this half page that I used. So obviously this increments is by 20, but this would only increments by 5. So obviously that could account for inaccuracies as well. But I think despite those errors or possible sources of errors, we still were able to meet the objective. I mean, for the line of best fit, we see that it's a positive linear line. It goes up. So you know that the bounce height and the drop height are then directly proportional. That is, when the drop height goes up, the bounce height goes up, and as you can see here in the points. So that was basically the objective that we found. We found that it's directly proportional. However, we know that because we don't live in a vacuum in the room, there is no vacuum here. There's always going to be gravity, therefore the bounce height is never going to go directly to where it was or back to where it was. So if you dropped it from 40, it was never going to go to 40 centimeters back up. It's always going to go a little less because of gravity. That's just the gravity laws. But I think this was a successful lab for my group and I, and we were definitely able to see that when you drop a ball, the proportions are direct and they keep going up. So I found this lab as a success.